Our next speaker in the workshop is Professor Gitta Kutyniok from LMU Munich. She will talk about the impact of AI on parametric PDEs. Gitta, the floor is yours.
Yeah, thanks a lot. So I think we all know how tremendously successful, let's say, the workhorse of AI, namely deep learning, is in public life. I mean, self-driving cars, telecommunications, speech recognition, legal issue, healthcare, which, I mean, unfortunately these days is much more important than it anyhow is. But then if we get a bit closer to science, we see that, I mean, there are breakthroughs which we could witness, for instance, just a couple of months ago, where AlphaFold 2, the new AlphaFold algorithm, basically, I mean, by far outperforms everything what has been done before concerning protein foldings. And now if you get even closer to, let's say, mathematical methods, then we see that it has a tremendous impact, in particular on inverse problems, the area of imaging sciences. So this was, I guess, to some extent, I mean, the first impact we regarded from the area of mathematics concerning deep learning. This started around 2012, and basically now, I mean, all different problem settings, denoising, edge detection, and so on are handled by these type of methods. Then partial differential equations were a bit slower to embrace these methods, and one can ask why. Well, I mean, the reason is that for a PDE, it's not initially clear why you actually need deep learning or neural networks to solve those. Because for inverse problems in imaging sciences, it's a bit more clear. You don't have a concrete model for what an image is, so that makes methods, learning methods, very effective. But here for the PDE, you actually have a rigorous physical model. So it's not clear why you need this, but what turned out, and what we also heard in the exciting 2 talks we just attended, that in the high dimensional regime, this is crucial, and their neural networks to some extent can beat the cross of dimensionality. Now, this all sounds very bright, but there are also still a lot of problems with these approaches. For instance, a lot of people might know deep learning was set equal to alchemy just basically 2 years ago. We're doing one of the plenary talks. Ali Rahimi stated that machine learning, in particular deep learning, is in a certain sense alchemy. But then if you look also a bit closer, you realize that there are indeed not only problems that you don't have, let's say, rigorous models, you have rigorous criteria how to choose architectures. But in fact, I mean, there are also other problems, for instance, with trustworthiness, where you can easily fool, to some extent, these type of algorithms. So therefore, to my mind, I mean, there are 2 directions one is currently pursuing and needs to pursue, which is on the one hand, mathematics for deep learning. So developing a deep mathematical understanding of deep learning, for instance, asking questions how to make it more robust. And then on the other hand, deep learning for mathematics. So in particular, as we already said, can we use deep learning, for instance, to improve imaging science applications? And also can we develop superior PD solvers using deep learning? So now let's delve a bit deeper into deep neural networks to set also the notation. I mean, we already in the previous 2 talks, we got definitions of what a neural network is, but also here, I mean, in the beginning, I need to fix notation, and I would also like to make you familiar with what, for me, let's say, the key theoretical research directions are these days. So this we already saw many times now. This is a neural network. It's a function from RD to some RNL, where NL is typically chosen equal to V1, for instance, in the classification setting. It's a highly structured function where you have affine linear maps with weight matrices and biases. And then you have an activation function, which is univariate and which you apply component-wise. And so key aspects are, for instance, the number of layers, which coincides with the number of affine linear functions. I mean, in truth, one has to be a bit more sophisticated. One actually should distinguish between the architecture of a neural network and then the realization of the architecture, which is then a function. But let's make it a bit more simple here and stick with this setting. Now, what are the key theoretical directions one can ask? I mean, first, for mathematics for deep learning, because we will then also use some of these ideas in the sequel of the talk. So for that, I would like to just very briefly, on a high level viewpoint, go through the stages, how we use neural networks, and from these, the key theoretical directions will arise. Now, what is the first stage? I think most of you certainly know we have a highly structured function in the background defined on a manifold, on a lower dimensional manifold. Let's say we have a classification function. For instance, here, computer scientists like to separate cats from dogs. So maybe here you have in one area dogs, which are mapped to the value 1, and cats, which are mapped to the value 2. And what you have are samples, which you then separate into a training and a test data set. Based on these samples, you want to learn, and so the first question already arises, which architecture to choose. So there were also some ideas in the previous 2 talks, but still at this point, I mean, let's say a comprehensive theory is missing how to choose the architecture in the best possible way. There are various results in this direction, but still, I mean, there are various open gaps in the theoretical foundation, as we'll see also later on. Yeah, and so, I mean, you need to ask how many layers to choose, how many neurons in each layer, which activation function. Maybe you want to pre-select certain entries of your weight matrices to be equal to 0, to already not immediately, or let's say first train a fully connected neural network, but to already specify a more ideal architecture. Then you train. So the training means learning the weights and the biases, which you do by an optimization problem, where you aim for that the neural network evaluated in your samples is close to your function values, and the closeness is given by a loss function. And then you can also, let's say, incorporate additional properties. So you have a regularization term where, for instance, you could place the little L1 norm on the weights and biases if you want to aim for sparse connectivity. You solve this by stochastic gradient descent, you get a neural network function, and then you hope that this function is close to your initial function. And the closeness you now test by the test data set. And so from this setup, I mean, from this, let's say, workflow, how you use neural networks, the key theoretical directions arise. The first being expressivity, which asks the question which aspects, for instance, of a neural network architecture affect the performance of deep learning, how to choose an architecture. So there we use methods, for instance, from approximation theory, applied harmonic analysis, and to some extent, this is the most developed theoretical direction at present, because it's also the one which already started when we still were dealing with shallow neural networks. And this is also the direction we will later on, when we come to parametric PDEs, also target, because some of the results will be of an expressivity type. The second is then the learning. So why does stochastic gradient descent converge to local minima despite the non-convexity of the problem, and let's say the difficulty of the energy landscape? And there are also exciting, I think, mathematical methods applied to this problem, even, let's say, methods like algebraic geometry. Generalization, why do neural networks not overfit? What is the role of depths? And also there are a different set of approaches and theories will come into play. And so these are the 3 directions of the 3 components. If we use this as a statistical learning problem, this is approximation, this is the error from the algorithm, and this is the error from that we just have sample values. And then there's another direction which I just find exciting, just as a side remark, which is explainability. You have a fixed neural network and you aim to reach a certain decision, and you're asking which features are most important for that. And there's basically no mathematics at present, but I think it's a very exciting direction. Now, so these are, to my mind, maybe the main directions concerning mathematics of deep learning. And as I said, I mean, we will then also derive results later on in the area of expressivity. But certainly to get a complete picture, you would also need to study learning and generalization. So then deep learning for mathematics, as I said, one direction are inverse problems. which also, in a certain sense, certainly belongs to the topic of this workshop concerning computational mathematics. So there the question in particular is, how can we optimally combine deep learning with previous methods, with model-based approaches? And as a general question, maybe a bit provocative, are neural networks capable of replacing highly specialized numerical algorithms? And this is not the main topic of this talk, but I mean, since all the talks are on PDEs, let me just use 2 slides to also show you concerning inverse problems what effect deep neural networks could have on that. And for that, I would like to choose this a medical imaging example, computed tomography, where one computes the radon transform. So what one does is we have our function, we compute line integrals through it. This gives me one slice of the so-called sinogram, and then I rotate. So I rotate this device, and each time I compute line integrals through it. This way I fill the sinogram, and from this you would like to recover the interior of the body. And this becomes a very hard problem. If you cannot do the full rotation, that means you have a whole block of data in your sinogram missing. That's called limited angle computed tomography. And so one approach which, for instance, we pursued, which is this philosophy of combining deep learning with classical methods, was we used model-based methods as far as they went. So we used sparse regularization with shearlets. And if you're not familiar with this, I don't have time to explain it, but it's sparse regularization is a particular approach to solve those problems. Then we used deep learning to complement this and carefully combine both, leading to results of that type, where here you have the original image, you have a 60-degree missing angle, and these are classical reconstructions. This is maybe very traditional reconstruction from this highly undersampled data. This is a bit better model-based reconstruction with still a lot of blurring here. This is using just a neural network, not combining with classical methods, and this is combining both. Yeah, and so you see, I think what you see here, I mean, just in this tiny example is that, and I think this is a general thread also in this research direction, that the best is to combine both worlds. First of all, deep learning are typically leads to better results than classical model-based methods, but then to combine both in, let's say, an appropriate manner usually gives the optimal results. Okay, so, but now, I mean, the focus of this talk is on partial differential equations. And so here we can ask again, I mean, the same question, the second question, the same as we ask here, this slightly provocative question: can we basically replace current methods with deep neural networks? Here we already saw in this little example, which I showed you, that this might at present not be a good idea. I mean, one cannot see in the future, but it seems that, I mean, certainly if we have physical knowledge, we need to use it. But here, in addition, the question is, why do neural networks perform that well in very high-dimensional environments? Okay, so let's enter the world of parametric PDEs. So here are my collaborators from TU Berlin, and then also Philipp Petersen from University of Vienna. Yeah, so parameter-dependent families of PDEs are widely used in, as I say here, basically any branch of science and engineering. So for instance, if you study complex design problems, inverse problems, optimization tasks, and so on, I mean, those problems can be phrased in terms of parametric PDEs. The family of parameters can be finite or infinite. Here we will always choose a finite family, and this is what the parametric PDE, let's say in abstract terms, looks like. So here we have our differential operator. The y is the parameter. The solution depends on the parameter, certainly, and also the right-hand side depends on the parameter, and also the parameters here maybe in a non-trivial way in addition involved. Yeah, so everything depends on the parameter y. Y comes, let's say, first, I mean, from an abstract space y. And what one then aims to solve is what's called the parametric map. We have a parameter, and for that parameter, we have a PDE, which we want to solve. So we want to map the parameter to the solution uy. And so the curse of dimensionality in a way hits here, for instance, if this y is very high dimensional. And the problem in addition is that usually this parametric map needs to compute many times, because if these are design parameters, then we might need to change the design slightly, compute the solution, need to change it again if we want to optimize over the design parameter. That means we have a multi-curious situation. Okay, so let's get a bit more into the details. So the next slide gives, let's say, a bit more specifications. If you're not familiar with all the details, don't worry. But I mean, for, let's say, the bit more experts, this might be very useful. So we look at this variational setting. So we have here a bilinear form by, and then we have v in our Hilbert space. So the capital Y, now our parameter space, sits in some Rp, and P is large, and this Y is compact. So H is the Hilbert space. The By here is bilinear form. It's symmetric, universally coercive, and uniformly continuous. The right-hand side, the Fy, is uniformly bounded and also well parameter dependent, as we already discussed before, and Uy is the solution. And in addition, for the results, we assume that the solution manifold, which is the set of all possible solutions, is compact. So these are technical assumptions, which, I mean, if you are not familiar with those, I mean, don't worry about that. Okay, so how do you usually solve such a PDE? Well, I mean, first you have the problem that you're in an infinite dimensional space. So to solve it first, I mean, we need to bring it down to finite dimensions anyhow. So for that, we choose, or it is typically chosen, a high fidelity discretization, meaning you have a subspace UH. The H stands for high fidelity. UH in your Hilbert space, where the dimension capital D will always be the dimension of the high fidelity discretization, is finite, but typically very large. And so this is then the solution of this. And so there's what's called Sear's lemma, which says that this solution is the best approximation of the true solution, of the continuous solution by elements of UH. And how do you get this solution? Let's assume I have a basis for my high fidelity discretization space UH. Then the solution of this can be written in this form. Yeah, so certainly it can be written in terms of my basis. That's clear because it's in the space. But what is interesting here is that the coefficients can be written in this way. So we have here what's called the stiffness matrix to the -1 times this FHY. Yeah, and you see, I mean, these are both, in a sense, discretizations of By, of your bilinear form, and of your right-hand side. Okay, so I mean, this is actually not that difficult to show, but one can just plug in here the basis, and it's basically immediate that you can get this form. Now, so now we can be a bit more concrete what we want to ask of our neural network. We have our parameter. Remember, this lives in our P, where P is very large. And we are asking now our parametric map. We can now write in this form, Y maps now to these coefficients. Now, so let's go back one slide to remind you. Yeah, so these are these coefficients here. And once we have them, we have the solution. Okay, so we have this map. So that, well, I mean, certainly this equation is true for any V. And what we now ask is, can a neural network approximate this parametric map? Why do we want to do that? Well, I mean, after we've trained it, the computation of the map is rapid, and also it's a very flexible and universal approach. And we see certain other advantages later on. So the question we now ask is, if we are given an accuracy epsilon, can we find a neural network which approximates this map up to epsilon for any parameter? That is an expressivity question. Yeah, it asks, does there exist a neural network which has this approximation capacity? And then we can also ask, and this is now, since I said in the high dimensional regime, we are interested whether neural networks can, let's say, circumvent the curse of dimensionality. We can now ask this neural network, how does the complexity depend on this P, which is this dimension of the parameter space, and capital D, which was our dimension from the high fidelity discretization. Yeah, and certainly what we hope is that this does not, for instance, depend exponentially on it. And then, as I said, I mean, this doesn't give us a complete picture. Yeah, remember I said, to get a complete picture, we need to understand expressivity, learning, and generalization. So here we just ask for expressivity. I mean, one can ask the other two questions, but I mean, this we could not solve yet. But then what we, in addition, we do extensive numerical tests and test how neural networks perform numerically on this task. I mean, certainly we are not the first to do that. You heard two beautiful talks about this topic. There's a long list, and I apologize for everyone I have not on the list here. So to solve PDEs with neural networks, just a very common approach is to approximate the solution by a neural network, but there are now very sophisticated different approaches how to incorporate neural networks in the training. And also for parametric PDEs, using neural networks, there are various approaches. Maybe the closest to our is the one by Schwab and Zech from 2018. Who considered, for instance, compared to us, a reduced basis of very special functions. So we are dealing here with a more general setting. Okay, so now, I mean, we need to ask an expressivity question. And for that, as I said, we need to understand then also what the complexity of the neural network is. So how do we measure complexity? This is just the definition from a neural network. We saw that before. The complexity we now measure by the number of weights. And what I mean by this is what we count are the number of non-zero entries of the weight matrices and the biases. So this is the number of non-zero parameters. And so, I mean, from a memory efficiency point of view, this seems to be an appropriate measure for the size of a neural network or the complexity. Now, concerning expressivity, there are already various results. We already saw some results in the previous talks. So there's, for instance, this famous approximation theorem, the universal approximation theorem, which says that if you have a continuous function on a compact set, rho is continuous, not a polynomial, then for every accuracy, I find a neural network, a very simple one, which just looks like this, a shallow neural network, which approximate this to this up to this accuracy. Okay, so this is a very classical result, but unfortunately the complexity, which is this n, the number of neurons, is here initially not in any way constrained. Then there are other results, for instance, from Jarodsky, who also has beautiful results concerning expressivity. And so this is one sample result where, for instance, he looked at S times continuously differentiable functions, where now the error in approximation can be indeed bounded by the complexity to the minus S over D. You see the complexity nicely comes into play here, but the dimension comes into play in a bit unfortunate way. Also, I mean, this is, for instance, not optimal. And then you can also ask about the function spaces, which are the right function spaces, which is also still an open question. We have some results in this direction, but I mean, what are natural function spaces for studying in general expressivity of neural networks is, I mean, not clear. But then if you would like to have optimality results, you need lower bounds. And so in that regime, for instance, let me mention two results. I mean, the first by Scham, Cloninger, and Kaufman. And then we built on their result and showed, for instance, that there exists a lower bound concerning the complexity of neural networks. And for certain classes of functions, you can construct complexity minimal neural networks which solve that task. But here, I mean, the concept of dimensionality comes not into play. So you see, I mean, in this area of expressivity, there are various directions, but still here, I mean, for our task, we can, well, use some elements of the previous result, but then need to study this problem anew. Okay, so this was our question. So we saw this before. This is what we want to approximate, this parametric map. And now we ask these questions, which we also saw before. We now know what we mean by complexity of a neural network. We mean the number of non-zero parameters, and we want to use a ReLU neural network. So for understanding a bit the result, let me also mention a classical methods which people used. And this was also already mentioned before, which is the reduced basis method. That's a classical method where people approach parametric PDE. And so what do they do? Here you see you have the continuous solutions, then you have the high fidelity discretization, and then this reduced basis method does the following. For certain parameters, you compute the solution, which takes a long time. That's the offline phase. And then online, for another y, you can compute it much faster using the previous solutions. Now, it's a bit also the philosophy, as you can imagine, of learning, where first you compute certain solutions and then you use those for training. Now let's be a bit more specific because we will need this notation then for our result. So what you do there is now you choose another space. You have first your high fidelity discretization space, and now you choose a reduced basis space, which has a much lower dimension, where here you see you have a dimension which we call d of epsilon, which is much smaller than the high fidelity discretization. Okay, so you have your continuous situation, the Hilbert space, the high fidelity discretization, capital D, and the reduced basis, which is little d of epsilon. Yeah, and you can choose that usually under certain circumstances, so that every continuous solution you can still approximate by elements from your reduced space. Yeah? So there's a whole theory in this direction, optimality, Kolmogorov width, and so on. So now what we need here is typically the reduced basis space. You can compute to some extent a basis. Let's assume I have a basis, and certainly this basis I can write in terms of the high fidelity basis. So I have my small basis, I have my large basis, I have this transformation matrix. Then certainly I can also compute the stiffness matrices for the reduced space by transforming the one from the high fidelity space down to the reduced space, and the same for the right-hand side. And the solution for the reduced basis space, I can write in terms of my basis for the reduced space. That's clear. I can write this basis in terms of the high fidelity basis. So I just use this here. So now I have written my solution for the reduced space in terms of the high fidelity basis. And then I can also now write this solution or the coefficient vectors for my solution for the reduced basis space as the inverse of the stiffness matrix and the right-hand side. So that's very similar to the high fidelity solution. In any case, so I can write this in terms of the high fidelity basis with this coefficient sequence. Okay, this, I mean, we will see in a moment again. So now this is our first result. Let's forget about the first part and let's just look here. What we can show is there exists a ReLU neural network of this size. And what you observe is that all the dimensions appear in a benign manner. So the capital D appears linearly. This was the high fidelity dimension, and the dimension of the reduced space appears cubically, and the P, which was the dimension of my parameter space, appears polynomially. So everything is nice. I don't see any, let's say, curse of dimensionality hitting here. And the neural network does what we want. It approximates the coefficients of my high fidelity solution. So it approximates the parametric map up to an epsilon for any parameter y. The hypotheses you need are here. This one is a very typical hypothesis, which is usually the hypothesis to assume that there exists a reduced space, a reduced basis space, which is in some sense natural. I mean, there should be some, let's say, some lower dimensional structure. Otherwise, the neural network, will not be able to sense it. And so then the cross of dimensionality might not be overcome. The second is a bit technical, additional technical condition where you see here the forward operator needs to be approximated by a neural network of a certain size, and also the right-hand side, but these are quite natural conditions. Where you have examples, and we'll see examples later on where this is satisfied. And so then, you can also do the same, let's say, for the continuous setting in certain circumstances where in addition you require that the neural networks approximate the solution, the basis of a reduced space. And again, you have a neural network which circumvents the cross of dimensionality. And so there are several equations which fulfill these requirements. I don't have time to go into the proof because I want to show you some numerical results, but let me mention what the key idea of the proof is. For that, I will go back 2 slides to this part. The key part of the proof is to create neural networks which approximate these vectors. So what you need to do for that is you need to go in certain stages. You first create neural networks which approximate the multiplication of scalars, the multiplication of matrices, the inversion of matrices, and so on. And each time you need to control the size of those neural networks. So it's very constructive as all results in the area of expressivity. Yeah, okay, I have it here. We approximate this by a neural network, we control its size. Okay, so let me now go into the numerical experiments. So what we just showed is there exists a neural network, but it doesn't tell us whether the training finds a neural network which does the job. So now, the problem typically is, for these approximation theoretical results, the bounds might be too tight. In reality, so because here we look at worst case results, in reality, it might be even better than these results seem to imply. But then we optimize, and stochastic gradient descent, is, let's say, not that understood at this point, how it affects our results. And also, in addition, we have asymptotic estimates. So it's not clear when the asymptotic is. So what we aim to do was through, let's say, very sophisticatedly set up numerical examples to analyze what these approximation theoretic effect of the architecture is. So if you set up, let's say, a series of tests, the problem to compare is certainly you need to understand the effect of the sampling procedure, the optimization procedure, how to quantify also the intrinsic complexity. And so what we did for that, we always took the same architecture. It's always the fixed architecture for all of those numerical experiments. We have independence on the sampling generation. Also, we have very, let's say, as it says here, semi-ordered test cases, as you will see in a moment. And we wanted to test 3 hypotheses for using these numerical experiments. The first hypothesis we wanted to test was that also the performance does not suffer from the cross of dimensionality. We saw this already theoretically, but now we wanted to test it numerically. that the performance is sensitive to parameterization. And also, so there are non-affinely parameterized problems, which are very difficult right now to solve, particularly using, for instance, reduced basis methods. And so the question was whether the learning is also effective for those problems. Again, we are not the first. There's a lot of literature on that. What I state here are some numerical studies for the learning for parametric PDEs, and also for studying the relation of approximation theoretic findings and practical examples. Okay, so, but what do we aim to do here? So we use the parametric diffusion equation, which you see here, on 0, 1 squared, and we aim to learn the parametric map. We'll see it in a bit more detail, and we vary various types: the parameterization, the dimension of the parameter space, and the complexity of certain high parameters, which we will see. So to go in a bit more detail, that's our parametric diffusion equation, which we aim to solve. So the A here is in AY, and the AY in the affine parameterization can be written in this way. So that's the parameter then here. And there are different types of parameterization, which again, I mean, I don't have time to go into all of the details. But there are, for instance, I mean, parameterizations which coincide with trigonometric polynomials, chess-Brownian partition, and also what's called cookies with fixed radii. So the level of difficulty grows. And then there are also non-affine parameterizations, which have a slightly different form, which are much more difficult. Then this is our setup. We always choose the same discretization of the space. So we choose 101 times 101 equidistant grid points. We choose a fixed neural network architecture, where here certainly our input dimension is the dimension of our parameter space. Then we have 11 layers, each time 300 neurons, and the last layer certainly coincides with the number of grid points, because we need to compute the value on each of these grid points. We choose a leaky ReLU, and each time we choose 20,000 IID parameter samples. We initialize our network always in the same way, which is always the same loss function, and the optimization procedure is also the same. And the dimensions can grow up to 91, which is already fairly large. So here are some of these numerical experiments. So this is, for instance, the easiest case, trigonometric polynomials. You see the definition of the parameters here, but let me walk you through the numerical results. You see here the parameter dimension and the mean relative test error. And what you observe is that there's a linear relation between the parameter dimension and the test error. It's the same for a bit more difficult affine parameterization, chess-Brownian partition. Again, you observe that's the key point here, this linear relation. There's no blow up, no exponential blow up. And also what one observed was that the training was also very benign. Yeah, so you see here the epochs and the mean relative error. I mean, there was a very nice convergence, which we observed each time. And then, I mean, the non-affine parameterized situation, again, you observe this relation between P and the relative test error. It is linear, and also here the training behaved in a very, very nice way, which was, I think, a bit surprising, because that's usually a very difficult situation. So in a summary, what we observed was to test our hypothesis. Indeed, it is true the performance from our numerical experiments judging does not suffer from the curve of dimensionality. Indeed, the performance is sensitive to the parameterization, and also the learning is effective, indeed, also for non-affinely parameterized problems. So in that sense, I mean, the approximation theoretic results already showed us in a very nice manner what might happen then concerning numerical experiments. So let me conclude, since the time is up. yeah, I think deep learning is an exciting area. There are two main directions: mathematics for deep learning for mathematics. Deep learning for mathematics, there are, to my mind, I mean, these two main threats for inverse problems and PDEs. We here dealt with PDEs, in particular parametric PDEs, where we saw and derived upper bounds on the complexity of ReLU neural networks to approximate these parametric maps. That was a result from the era of expressivity. And then I showed you extensive numerical experiments, which showed that indeed what we found theoretically can be also witnessed numerically. And so in general, let me just finish with this, because I think there are various key directions or key problems in deep learning, which opens, let's say, an exciting new area. And so judging from what the results and the directions I showed you before, what are the key, to my mind, the key problems? What is the role of the depths for neural networks? Then what are the aspects of neural network architecture? So the expressivity question, why does stochastic gradient descent converge? That would be a learning question. Why do neural networks not overfit? So generalization questions. And then these questions would be more in the direction of deep learning for mathematics. So what about high dimensional environment? Which features are learned? And maybe, as I said, provocative, are neural networks capable of replacing highly specialized numerical algorithms? Maybe not at this point. I don't know, maybe in the future, we'll see. So I think there are very exciting future perspectives. And with this, I'd like to thank you very much for your attention.
Thanks, Gitta, for the great talk. We have some time for questions. I think Lenka put a question in the chat already. Lenka, do you want to unmute yourself?
Okay, let's do that. Thank you, Gitta. I missed in the experiments, what was your stopping criteria in the plots where you have the error as a function of the number of parameters?
So, you mean here?
Yeah, for instance, like at the end.
So the stopping criteria was then typically to so the mean relative error, so that we wanted to go below a mean relative error. So that was the stopping criteria.
You mean you have a value of mean relative error, but there's not a test error. Sorry, I'm a bit confused. On the right-hand side, there's the test error.
So let me see. Yeah, so let me remember what we did there. I think, yeah, so if I remember correctly, we always went through, I think. I think we always went through a certain number of epochs. So what you see here is, you see, I mean, there are always 40,000 epochs here and here. So for these results, and so if I'm not mistaken, yeah, exactly, this is right. So this was then the stopping criteria to make all the experiments comparable. Yeah, but yeah, I think it was that. But I mean, yeah, if I remember correctly. I mean, I can, if I remember correctly, that was the stopping criteria. But
so I was like, just to understand, I mean, I understand you demonstrate here kind of the lack of the curse of dimensionality, but how good is this performance? Like, for instance, if for the very same setting with that dimension P, I run some standard solver, what is the error I would get? Much smaller or comparable, or the question doesn't make sense?
So here, I mean, in the affine situation, I mean, I wouldn't say that right now neural networks are better than that. Yeah, so here, I mean, the goal of these numerical experiments was first just to test whether what we observe theoretically can be also witnessed numerically. Yeah, so this was the goal. It was at this point not to outperform current other methods. Now, for these in the non-affine situation, there, I mean, from what I know, I mean, I'm also not an expert in, let's say, PDEs, but there, I mean, the non-affine situation methods like reduced basis don't work. So in that sense, I mean, here, neural networks have an edge. For these settings, it is at this point a test whether the theoretical results point in the right direction. Because, I mean, you also need to think that PDE solvers, I mean, are right now, I mean, very sophisticated. People have worked on there for many years. So in that sense, I mean, it is not that easy to immediately outperform those. And here, as I said, I mean, the goal of this experiment was also not to outperform that, but to test these hypotheses which we saw theoretically.
Yeah, no, I understand that. It was just to have an idea how you know, whether it's 10 times smaller, the state-of-the-art error, or just a bit. Or
yeah, I mean, I don't have any, let's say, comparison to that to that here, because it's a very different, let's say, algorithm and setup. But yeah, so this is what I can tell you about it.
okay, thanks.
Okay. Other questions from the audience? So there was a question by Simone Pakila. So do you want to unmute yourself?
Can you hear me? Can you hear me?
Yes.
Hi. Thanks a lot for the great talk. I just wanted to know if you think that like the concern of instabilities, like adversarial attacks, can be a problem, a real issue in the setting for parametric PDEs. What are your thoughts in this respect? Thank you.
Yeah, well, I mean, that's I think a very good question. I mean, I cannot give a, let's say, completely comprehensive answer. I mean, from our, let's say, experiments, as you see here, I mean, it's, yeah, so the convergence is nice. There, we also didn't observe any, let's say, outliers or any adversarial examples, but I mean, this can always happen. I don't think you can exclude that. So asking if it's a problem here, I mean, I can only say we didn't observe this problem, but it could be that, I mean, the problem could certainly happen. We cannot exclude it. So that's the best I can say.
Okay, thank you.
Okay, so if there are no further questions, let's thank Professor Gitta Kutyniok again for the nice talk. Our next speaker is Professor Michael Brenner. Michael, could you share your slides?